Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have rectangle ABCD. Side AD of this rectangle equals to 3 units in its length. Inside this rectangle we have two semicircles. Those two semicircles, the radius of this big semicircle is equals to 2 units. The radius of this small semicircle equals to 1 unit in its length. Again, our mission is to find out the length of this line segment AE. So first of all, we know that all the angles inside any rectangle are right angles. So those four angles are all right angles. So actually this is a right angle. And this is angle ADC. That is also a right angle. Angle BCD is a right angle. And finally, this is angle ABC, that is also a right angle. In the next step, we will define the relevant points to this question with letters. We will define the center of this big semicircle. This point is point P. Likewise, we will define the center of this small semicircle. This point is point Q. We define the touching point of those two semicircles. This point is point S. We will define the point of tendency of tangent AE with this big semicircle. This point is point L. And finally, we will define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction, that is to say, we will extend side DC of the rectangle and side AE by a straight line until they touch each other. Actually, this is their touching point. We will define their touching point. This point is point F. DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend a straight line by a straight line, the result must be a straight line. Therefore, DF is a straight line. We'll focus on the upper side of this straight line DF at point C. Here, the sum of the angles must be equal to 180 degrees. According to rule 3, that said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We focus on the right small triangle ECF. We define this angle EFC as alpha. So in the right small triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle ADF. In the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. Okay. So here we have the radius PL that is equal to 2. The radius PL is drawn to point L, that is the point of tendency of tangent AE with this big semicircle. And here we can implement rule 1. According to rule 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AEB that is tangent to this circle at point M. Point M is the point of tendency of tangent AM with this circle. In addition, we have the radius OM. The radius OM is equals to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing, if we focus on the big semicircle, we have the radius PL that is on to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is on to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius GQ of the small semicircle. The radius GQ is equals to 1 is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So in the small right triangle GQF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertice angle must be equal to 90 degrees minus alpha. Likewise, we focus on the big right triangle LPF. In the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this vertice angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So in the next step, we will prove that the big right triangle LPF is similar to this small right triangle GQF. So write it down. We will prove that the big right triangle LPF is similar to the small right triangle GQF. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this is angle PLF, in the big right triangle LPF, and this equals to this angle, that is actually angle QGF, and the small right triangle FGQ. Open again. Angle PLF in the right big triangle PLF equals to angle QGF in the small right triangle FGQ. They are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, as it is belongs to the big right triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to angle alpha as it is belongs to the small right triangle QGF, it will be defined as angle GFQ. Repeat again. This equation means that angle alpha equals to itself. So we just call to angle alpha two different names. Angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle LPF. In the big right triangle PLF, and it is equals to this angle, that is actually angle GQF. In the small right triangle FGQ. So repeat again, if we found out that angle LPF in the big right triangle PLF equals to angle GQF in the small right triangle FGQ, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we proved that all the three angles in the big right triangle LPF are correspondingly equal to all the three angles in this small right triangle GQF. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. If we found out that the big right triangle LPF is similar, this is the sign of similar, to the right small triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP, the big triangle PLF, or side GQ in the small right triangle FGQ, equals to side PF in the big right triangle LPF, over side QF in the small right triangle FGQ. So I repeat again. We derive that side LP in the big right triangle LPF, or side GQ in the small right triangle FGQ equals to side PF in the big right triangle LPF, or side QF in the small right triangle GFQ. What is the length of PD? PD is the radius of this big semicircle, that is equals to 2. PS is also the radius of this semicircle, the big semicircle, that is equals to 2. Likewise, we have the radius QS of this small semicircle, that is equals to 1. QC is also the radius of this semicircle, that is This is equal to 1 unit in Islam. And finally, we have line segment CF that is unknown. So we define the length of line segment CF as x. So actually found out that LP over GQ equals to PF over QF. LP is the radius of this big semicircle, that is equals to 2 over GQ. GQ is the radius of this small semicircle, that is equal to 1, and it is equals to PF. What is the length of PF? PF in total equals to 2 plus 1 plus 1, that is 4, plus x. Again, PF in total equals to 2 plus 1 plus 1, that is 4, plus x. So in total PF equals to 4 plus x. Over QF. QF in total equals to 1 plus x. In conclusion, we found out that 2 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And we get that 2 times 1 plus x equals to 4 plus x. Here we'll open the brackets on this side of the equation and we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation and we get that 2x minus x is x. So in this side of the equation we have x plus 2 is equals to 4. Here we subtract 2 from this equation, and finally you get that x equals to 4 minus 2 is 2, so x equals to 2 units in its length. So line segment CF that is equals to x is equals to 2 units. So I write it down. In the next step, we will prove that the big right triangle ADF, the biggest right triangle ADF, in this domain, is similar to the smallest right triangle in this domain, that is triangle ECF. So that is on, we prove that the big right triangle ADF is similar to the small right triangle ECF. So why the biggest right triangle ADF is similar to the smallest right triangle ECF? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle ADF. In the big right triangle ADF, and it is equal to this angle, that is actually angle ECF. The small right triangle ECF. So actually again, if I found out that angle ADF in the big right triangle ADF equals to angle ECF in the small right triangle CEF. They are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha. This is angle alpha, that is the common angle that belongs to both triangles. So you can write down that angle alpha equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle alpha, since it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if we relate to this angle alpha, since it belongs to the small right triangle CEF, it will be defined as angle EFC. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle DAF. In the big right triangle EFT, and it is equal to this angle, that is actually angle CEF. This one right triangle ECF. Repeat again, if you found out that angle DAF in the big right triangle AFD equals to angle CEF in the small right triangle ECF. They are both equal to 90 degrees on some part, therefore they are equal to each other. So we actually proved that all the triangles in this big right triangle ADF are correspondingly equal to all the triangles in this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If we found out that the big right triangle ADF similar, this is the sign of similar to the small right triangle ECF according to angle similarity rule. And from the fact that the biggest right triangle is similar to the smallest right triangle, we derive that the following relationship exists between their sides. We derive that side AD, the big right triangle ADF, over side EC in the small right triangle ECF, equals to side DF in the big right triangle ADF, over side CF in the small right triangle ECF. So repeat again. We will derive that side AD in the big triangle over side EC in the small triangle equals to side DF in the big triangle over side CF in the small triangle. AD equals to 3, therefore we solve AD by 3 over EC. EC is the missing side, so we leave it as it is, and it is equals to DF. What is the length of DF? DF in total will be equal to 2 plus 2 plus 2, that is 6, plus 1 plus 1, so 6 plus 2 is 8. So in total DF equals to 8. Over CF. CF equals to 2. So in conclusion, if we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So if we found out that 3 over EC equals to 4, here we multiply this equation by EC, finding out that 3 equals to 4 times EC. Here we divide this equation by 4 and finding out that the missing side EC equals to either 3/4 or to 0.75 units in its length. So actually, this is the missing side AC. It is equals to either 3/4 or to 0.75 units. What is the length of side BC of rectangle ABCD? According to the rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle ABCD, side AD must be equal to the opposite side BC. But AD is 3, therefore BC must be also equal to 3. So, what is known that BC equals to 3 units in its length. So, what is the length of this missing 97 BE? 97 BE will be equal to BC minus EC again. BC minus EC equals to BE. So I want to know that missing 97 BE is equals to BC minus EC. So BE equals to BC. BC is 3 minus EC. We just like the formula that EC equals to 0.75. So in total, BE equals to 3 minus 0.75 is 2.25 units. So BE equals to 2.25 units. What is the length of side AB? What is the length of side AB of this rectangle ABCD? According to the same rule that the opposite sides of a rectangle are equal to each other, we get that side AB must be equal to the opposite side DC. And DC equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So DC equals to 6, therefore AB, the opposite side AB must be also equal to 6 units in its length. In the next step, we copy the right green triangle ABE in a new page, and we implement the Pythagoras theorem on this right green triangle ABE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. Side AB equals to 6 units in its length, and side B equals to 2.25 units. So actually, this is the green right triangle ABE that I got from the original drawing. According to the Pythagoras theorem, this right triangle ABE, AE squared, that is the square of the hypotenuse, equals to AB squared plus BE squared. So I write it down. So AE squared equals to AB squared plus BE squared. The hypotenuse AE is the missing side, so we leave it as it is. AE squared equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. Check it again. Okay, so if I found out that AE square equals to 36 plus 5.0625. So AE square equals to 36 plus 5.0625 equals to 41.0625. So here we take out of this equation and finally we get that the missing line segment AE, the line segment that we are looking for, is equals to the square root of 41.0625. This is actually equals to 6.408 units. That is the answer to the question. So I repeat again, if we found out that the length of line segment AE is equals to 6.408 units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the length of this line segment AE. So in that moment, we have rectangle ABCD. We know that side AD of this rectangle equals to 3 units in its length. In addition, inside this rectangle, we have those two semicircles. The radius of this big semicircle is 2, the radius of this small semicircle is 1. Again, our mission is to find out the length of this line segment AE. So first of all, because of the fact that ABCD is a rectangle, all those 4 angles inside the rectangle are right angles. This one in any rectangle, and especially in rectangle ABCD. In the next step, we actually defined the relevant points to this question with letters. We defined the center of this big semicircle, this point is point P. We defined the center of this small semicircle, this point is point Q. Likewise, we defined the touching point of those two semicircles, this point is point S. We defined the point of tendency of tangent AE with this big semicircle, this point is point L. Likewise, we define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did the construction, that is to say, we extended line segment AE and side DC of the rectangle by a side line until they touch each other. This is the touching point. We defined this touching point between the side DC and the extended AE is point F. So actually DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then we extended the straight line DC by a straight line, and the result is DF. When you extend a straight line by a straight line, the result must be a straight line. So DF is also a straight line. So if we focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of DF at point C? We have this angle that is right angle plus this missing angle. In total it must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in size. Okay, so now we focus on the small right angle ECF. In the small right angle ECF we define this angle EFC is alpha. So in the right front triangle ECF, this angle equals to alpha, this angle equals to 90 degrees. Therefore this one is angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the symbol that says that the sum of the angles in any triangle is equal to 180 degrees. Okay. Now we know that dP is the radius of this big semicircle, that is 2. PS is also the radius of this big semicircle, that is 2. SQ is the radius of this small semicircle, that is 1. Likewise, QC is also the radius of this small semicircle, that is 1. CF is the unknown line segment, so we define the length of line segment CF as x. Now, actually have the radius PL, that is 1 to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have radius that is 1 to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius QG, that is 1 to point G, that is the point of tendency of tangent AE with this small semicircle. Whenever your radius that is 1 to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule 1. So in this small right triangle QGF, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle LPF, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha according to the symbol that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the right big triangle LPF is similar to this small right triangle QGF. So when those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the triangles of the big right triangle LPF are correspondingly equal to all the triangles of the right small triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. Again, I should found out that the big right triangle LPF is similar, this is the sign of similar, to the small right triangle GQF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. Repeat again, we will derive that LP over GQ equals to PF over QF. LP is 2, GQ is 1, PF, what is the length of PF? PF in total equals to 2 plus 1 plus 1, that is 4, plus x. So PF equals to 4 plus x over QF. QF in total equals to 1 plus x. So in conclusion, we found out that 2 over 1 equals to 4 plus x over 1 plus x. Here we multiply this equation by 1 plus x. And finally found out, okay, that 2 times 1 plus x equals to 4 plus x. Here we open the brackets on this side of the equation. And finally found out that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation. And finally found out that 2x minus x is x. So in this side of the equation we have to leave x plus 2 equals to 4. Here we subtract 2 from this equation. And finally found out that x equals to 4 minus 2, that is 2. So this line segment CF is equals to x, according to our definition, is equals to 2 units. Okay? So in the next step, we proved that the biggest right triangle ADF is similar to the smallest right triangle ACF. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees and therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles. So I can write down that angle alpha equals to itself is a common angle that belongs to both angles, and finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the figures of the big right triangle NDF are correspondingly equal to all the figures of this one right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. Once again, if we found out that the big right triangle ADF is similar to the small right triangle ECF according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD of the big triangle or side EC of the small triangle equals to side DF of the big triangle or side CF of the small triangle. Okay, again, we derive that AD over EC equals to DF over CF. AD is 3, EC is the missing side, so we leave it as it is, over DF. DF in total equals to 2 plus 2 plus 2, that is 6, plus 1 plus 1, so in total it is 8. So DF equals to 8, and CF equals to 2. So in total we found out that 3 over EC equals to 8 over 2. 8 over 2 is 4, so we found out that 3 over EC equals to 4. Here we multiply this equation by EC, and we found out that 3 equals to 4 times EC. So here we divided this equation by 4, and we found out that the missing line segment EC is equals to either 3/4 or 0.75. So this is the missing line segment EC is equals to either 3/4 or 0.75. What is the length of BC? According to the rule that the opposite sides of a rectangle are equal to each other. So in rectangle, we get that in rectangle ABCD, side AD must be equal to the opposite side BC, but AD is 3, therefore BC must be also equal to 3. Here BC equals to 3. So what is the length of this missing line segment BE? From the moment is right to see that BE equals to BC minus CC. Again, BC minus CC equals to BE. Again, B equals to BC minus CC. So B equals to BC, that is 3, minus CC, that is 0.75. So in total, B equals to 3 minus 0.75, that is 2.25. B equals to 2.25 units in its length. So here we use again the rule that the opposite sides of a rectangle are equal to each other. So rectangle ABCD, side AB must be equal to the opposite side DC. But DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is 2, and 4 plus 2 is 6. So in total DC equals to 6. And the opposite side AB must be equal to the opposite side DC. And DC is 6, therefore AB must be also equal to 6. In the next step, I copied the right green triangle, this right green triangle AB in the new page, and implemented the Pythagoras theorem in this right green triangle ABE. So this is the right green triangle ABE that according to the drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle AB is AE, and therefore the square of the hypotenuse is AE squared, and AE squared must be equal to AB squared plus BE squared. Again, AE squared equals to AB squared plus BE squared. AE is the missing side, so we leave it as it is. So AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25 squared, that is 5.0625. So in total, AE squared equals to 36 plus 5.0625. 36 plus 5.0625 is 41.0625. So in conclusion, we found out that AE squared equals to 41.0625. Here we took out of this equation and finally found out that the missing line segment, the line segment that we are looking for, line segment AE, is equals to the square root of 41.0625, that is actually equals to 6.40 8 units. Repeat again. We found out that the length of this 970 AE is equal to 6.408 units. Okay, thank you very much.